So today we're learning all about Newton's third law, which we just had an intro to in our bell ringer, and we're learning about momentum. Okay, our objectives for today: you'll be able to describe Newton's third law and apply it to situations. You will be able to explain why action-reaction pairs do not cancel each other, and you will be able to calculate momentum for a situation. So there's a formula for calculating momentum, and then there's also tricks for calculating momentum during collisions. So in both situations, you'll be able to calculate momentum. And then finally, you'll be able to explain for me in what situations momentum is conserved. All right, we're going to get started. Newton's third law, as we just saw in the video, when one object exerts a force on a second object, the second object exerts an equal and opposite force, or an equal force in the opposite direction on that first object. Because of this law, we know that forces are always going to come in pairs. So you're not just going to have one isolated force. If I am pulling on a rope, the rope is pulling back on me. There is an action force, that's the force exerted by one object on the other. And there is a reaction force, which is the force exerted back on that object by that object. So, for example, action force, I push on the wall. Reaction force, the wall pushes on me. Okay. A lot of times, people confuse the result of the force as the reaction force. So if I kick a ball, that's the action force. The ball applies an equal and opposite force on my foot, okay? That's the reaction force. The ball moving is not the reaction force. The reaction force is always in the opposite direction and on the object that applied the initial force, okay? So these forces are equal in strength. So if the action force is 10 newtons, the reaction force is 10 newtons. But they are opposite in direction. They don't cancel out because they are happening to different objects. So far, we have talked about forces on one object. So if we had an object that was receiving a 10 Newton force from this direction and a 10 Newton force from this direction, what would be the net force on this object? Zero newtons, because the 10s are pushing in opposite directions, so they cancel out. So why don't action-reaction pairs cancel out? Well, it comes down to one simple thing, and let me draw you a picture to illustrate. Okay? If this box is pushing on this box with a 10 Newton force, then this box is going to push on that box with a 10 Newton force. Okay? So we still have 10 Newton forces acting in opposite directions. So why aren't these canceling each other out? Because it's two objects, okay? The object on the left is one object receiving two forces that are acting in opposite directions. But if we were to isolate this out, it's two objects and they each only have one force on them. So why would those forces cancel? They're acting on entirely different objects. Okay? That is why they don't cancel out. In action-reaction pairs, the forces are equal in strength and opposite in direction, but they are happening to different objects. So they do not cancel each other out. We only total forces for net force on individual objects, not on systems of objects. So because they are happening to different objects, those forces do not cancel. Here are some examples of action-reaction pairs in action so that you can get sort of accustomed to what is an action force and what is a reaction force. Okay. First off, we have a swimmer here, okay? If you are swimming, when you move your arm through the water, you are pushing on the water. That is our action force. What do we think the reaction force is? Exactly. The water pushes back on you with the same force. Okay? So you push on the water pushes on you. Because the whole entire swimming pool of water has significantly more mass and therefore more inertia, the result of this force pair is you experience movement because of it and the water not so much. It's the same thing as when we went back to the example from our bell ringer video about the Earth and the Moon. The force that the Earth applies to the Moon is the same strength as the force that the Moon applies to the Earth. However, the Earth has significantly more mass and therefore much more inertia than the Moon, which means that the same force applied to it will not move it as far. It will move it a little bit in its orbit, just a little wobble, whereas the same force applied to the Moon, which has much less mass, will cause it to move more. Okay? So think about it in terms of a soccer ball versus a bowling ball. If you apply the same force to a soccer ball that you apply to a bowling ball, which one will move more? The soccer ball. It has less mass and therefore less inertia. Okay, so just because forces are equal and opposite doesn't mean that the result of those forces is always the same. Okay. Here's another example. If the reaction force is greater than the force of fluid friction, the net force is forward and you move through the water. That's how we're able to move in the water. Another example. Action force. You push down on the ground. Reaction force. The ground pushes up on you with an equal force in the opposite direction. If you push hard enough, the reaction force is greater than the downward force of gravity and you move upward. The Earth doesn't move a visible amount because it has so much more inertia than you that the force you apply to it doesn't really move it, but the same force applied to you is more than enough to move you, so you move upward. And our final example of a rocket ship. Burning rocket fuel produces hot gases, which the engine pushes out in a downward direction. The gases also push on the engine, and they push with an equal and opposite force. So while the gases are being pushed down, the rocket ship is being pushed up. If the force of the gas pushing on the engine becomes greater than the force of gravity pushing on the rocket, then the rocket will fly upwards. This is coincidentally the reason why rocket ships still work in outer space. If rocket ships were having to push on the Earth or push on the atmosphere to move them, as soon as they got into empty space, they would stop being able to fly. But because they're relying on an action-reaction pair, gases get pushed out, gases push on the rocket continues to be able to fly even in outer space where there's not matter around it. Now let's talk about momentum. That's the next thing on our list of objectives, okay? Momentum is a measure of how hard it is to stop a moving object. And it's a useful way to describe changes in motion due to action-reaction forces. Our equation for momentum is momentum, which is measured in kilograms times meters per second, is equal to mass, which we'll usually measure in kilograms, times velocity, which is measured in meters per second. Okay. You'll see it written as P equals M times V. We abbreviate momentum with the letter P instead of M because we already abbreviate mass with the letter M. And we can't have two variables that are the same in an equation. It gets confusing. So momentum is abbreviated with the letter P, and it is equal to mass times velocity. Let's do an example. Calculate for me the momentum of a 12 kilogram bicycle that is moving at 5.5 meters per second. Go ahead and try it on your own, then we will do it as a class. So let's talk about what we know. we know mass, right? That's 12 kilograms. We know velocity, it's 5.5 meters per second. And then they want us to solve for momentum. We don't know what that is. So the equation we're going to use is momentum is equal to mass times velocity. So we're just going to plug in mass times velocity. And that comes out to what? When we take 12 times 5.5, we get 66. And then your unit is going to be kilograms times meters per second. There's your answer. Okay. Large objects, because they have more mass, are going to have more momentum and therefore are going to be harder to stop. If the net force on an object is 0, then the velocity does not change. And if the velocity doesn't change, then the momentum on an object doesn't change either. Because force equals mass times its change in velocity, force also equals changes in momentum. Anytime objects collide, momentum is going to be transferred from one object to the other object during a collision. The law of conservation of momentum states that the total momentum of a group of objects stays the same unless outside forces act on the objects. So imagine a set of billiard balls. Okay, they're set up for you to start the game, and you hit the cue ball, and the cue ball strikes all of those billiard balls. Okay? If we are ignoring friction, okay, then the momentum of the cue ball is going to be transferred into all of those other balls, and the total momentum of the system will stay the same. Of course, here on Earth, collisions aren't always perfect like that, and we often lose some momentum to friction and other outside forces, but in a system where there are no outside forces, momentum is going to remain the same. There are two types of collisions that objects might experience. Okay? The first is elastic, which means the objects bounce off of each other. Example, the pool balls that I just talked about. Okay? You hit the cue ball into another billiard ball, that ball's going to move, but the cue ball's also going to move backwards a little bit. They hit each other and then they move away from each other. Or there is an inelastic collision where objects stick together. So, for example, if one football player runs and tackles another, they become one mass and collapse to the ground together. They collided, but they did not move apart from each other. So it is an inelastic collision. In all types of collisions, both elastic and inelastic, momentum is going to be conserved. Okay? So if you have those two football players running, they each have their own momentums, right? When they collide and stick together, their final momentum should be a combination of the two momentums they started with, because that momentum is being conserved. It doesn't just disappear. All right, this is where our notes end for today. Your homework is the 2.4 check for understanding.